recording.
And right now I don't care about this, but then looking at the top of the list, I see in this case Seedlint in code 203 is where I'm spending most of my time. So 7979 out of the 9752 samples, I was in Seedlint. So Seedlint is where all my CPU service time is going, and it's showing 239 seconds in Seedlint. So that's the main subroutine I'd be interested in. It's about 81%, 82% of the service time of my program. Okay, so that was out of the 292, 239 was in that subroutine. And I do have a JA report here, and here we are, 293.35, and under Perfex, or I'm sorry, under this one, we had 239 or 292.56. So it missed a little bit, just a little bit of difference there. But that's due to polling, due to the sample rate. If I'd gone to 1 millisecond samples instead of 30 millisecond samples, then they'd be closer. Now the next one I was going to look at now was my perf report. Compilation, and here's my perf report. Now it's wrapping kind of bad here. You get the large fonts. But here we are. It's basically coming out at 288 seconds for this particular run. Any other data? I'm going to go down to the end and see what it showed later. 290, all right, right here, 288.57. So that's what we're getting up here. 288.50, pretty close. Okay, and at the top of the list right now is graduated floating point instructions. That's good. 122 seconds of the 288 was doing computational work. Then I had 114 seconds where I was missing primary data cache. Then I've got my loads and my stores. Everything I read and write to memory has to get loaded and stored. And then I've got my quad words moved to primary data cache. Secondary data cache misses only 18 seconds during that particular run. So if I was to compare this and run this 5 different times, let's see if we can do that here. Grep. I want the event. Let's go with the secondary data cache misses events. It's 26 right here. I've only got one report there, I guess, that's showing that. 18.5 seconds. I was going to try to look at a whole bunch. Now. Question?
Do you get in all of this off when you just ran your programs?
Yeah.
Because I'm not getting into the profile line.
In the PR? Oh, you don't get the profile if it's killed.
Oh, in the PR one, okay.
So some of your code 2 MPs that had the user sig 2, they might not have a report to them because they got killed.
Here it is.
Find where now? So the PR was the profile ones, and then the PE was the Perfex ones. Now, I'm going to turn down the lights for this. This way. I have a script that I run to stress test the bottleneck behavior of the application. Now, in the compute server market, this is causing a large variance in our CPU service time. So people are always asking, I run the application, I get all these different numbers. Why do I get all these different timing numbers? So I run an experiment that basically starts off with one copy of code 2, and then it goes 2 copies, 3 copies, 4 copies, all the way up to 64 concurrent copies like we did yesterday. And then I grab the Perfex data for all those reports and then pull out the timing numbers that we were just looking at. And out of that, I've got a plot here now that's going to show system cache thrash effects. So each one of these lines is a Perfex report. I've got over 4,000 Perfex reports here. This experiment runs overnight. I come back in the next morning and then take a look at the data. So I go into a flat file. I basically bottle dump all the Perfex reports into standard error and then prepping off the data, the fields that we were just looking at, out of all these Perfex reports. At this end, I am running 1 copy of code 2. And at this end, I am running 64 copies of code 2. So there are 64 code 2 reports in this particular area here. 64 data points representing the service times for these 64 runs of code 2. And they're all running concurrently. Question? Okay. So down here is 1 copy. Remember that bottleneck curve I showed you? Right here is where I'm getting to 16 copies on a 16 CPU system. And once I go more processes than CPUs, all my service times are going up as well. Now note this is the exact same program, code 2. And floating points are the yellows, and they are staying flat. The computational work is not changing. Now there is a little bit of variance on these lines, and that's due to the fact that I'm using -A. There's going to be a little bit of distortion on the numbers because I'm multiplexing the port to get to these numbers. But the trend is very clear. Once I get above a certain number of CPUs, so you're 16, 17, 18, 19, 20, 21, 22, 23, 24, etc. In fact, you can even spot here 16. This is probably 32 right there. You can actually see where it switches depending upon whether the length is even or odd. So this is probably the point where it actually gets 2 times more processes than number of CPUs. So my service time is going up anywhere from 288. In one case, it was in the 420-second range for the exact same amount of work. And floating points are staying flat. So are things like instruction cache misses. There are only 2 metrics that are going up. There are only 2 metrics that correlate with this. I'm going to zoom down into this lower data here. And there they are. So once I hit the number of CPUs, there are 2 counters that are going to go up in correlation with SAR-Q. So this is showing SAR-Q as SAR-Q is going higher. Okay. So what we're looking at here is this one, system cache thrash effects, where SAR-Q is greater than the number of CPUs. Okay. So this is actually measuring system cache thrash, and Linux will have the same problem. Any cache-based machine is going to have the same problem. The bigger the cache, the more the problem. So if I have 8 megabyte caches and I load them up, it's going to be the same sort of problem. But fortunately, the clocks are getting faster on the secondary caches too, not just the size, but the clocks as well. So this is system cache thrash, and the only thing I can do to avoid that is to lock it down into a CPU and not let anybody else share that secondary cache. Now let me show you the same application, and this time I did it on a larger system, but I also did it under Miser, and Miser guarantees me my CPUs. And at the same time I did it in Miser, I also did it outside of Miser. So these 2 job mixes were running at the same time. And also, let me get that other one I had up here. So Perfex data isn't much good on its own, but when you've got it in combination, with enough samples to look for the trends. So here was that same workload running inside of Miser, note a very repeatable, predictable timing until we get up to here. These are from check config daemons. Just like when I was down in here, before I hit the number of CPUs, you can see right here is where I'm oversubscribed, but in here I still have one or two stragglers. My bottleneck is starting to cave in quicker. And that's from, again, check config daemons, or in particular, real-time daemons. So here, I've got real-time daemons that are kicking me out because real-time will always run before Miser. But this class is running outside of Miser, no guarantee on the CPU, so it's in a wide open system, and the scheduler is going to thrash it all over the CPUs. And again, you can see where I hit my number of CPUs on the system. Once I hit that bump, all my processes went up a little bit. But there were still some effects going on here because I was running with interactive users that were also running applications. So I started getting system cache thrash effects before I hit the number of CPUs on my system. But the stuff inside of Miser was much more repeatable except for the stuff that was real-time related. And again, if you go down into the data, the two that correlated with it are secondary data cache misses and quad words moved to secondary cache. So by looking at my Perfx report, I can spot these different types of effects. So we looked a little bit at TOB misses, that was in the workbook examples, and right now we're looking at secondary data cache misses, in particular system cache thrash. These other things are related to the application. This one's related to the CPU scheduler. And we're not multi-threading yet, so the false cache sharing isn't showing up yet. Or barrier synchronization. So right now, we're actually seeing this particular effect, system cache thrashing. Again, I'm just going to go down in here. And the two that correlate, I've got this one here, which is my secondary data cache misses, and this one here, that's my quad words moved to secondary data cache. And those are the two that are going to correlate to my varying service times. So imagine a person that's charging for this, and I run it once, it's 200 seconds, I run it again, it's 600 seconds for the same amount of work. And they're going to get twice the bill, and they're not going to like it. Now we're going to come back to CPU scheduling later. Run-on can also do the same thing, lock it down. A couple other things that we can do with CPU sets and stuff that can lock it down and make it private.
I've got 7 of the PEs. We range from 26 to 44 seconds.
Yeah. So that's showing you the variance. So that I was visualizing that same set of numbers for 4,000 of those instead of 4 or 5. But if I run it 10 times, those are the two numbers that I'm going to look for my variance from run to run. And if I can get that out of the way and lock it down to the 288 where it should be, this program, single threaded, should stay at 288. Okay, no matter what the load is on the system, the service time should stay at 288. So when the system load starts going up, my service times get longer, my throughput goes down, I'm getting less work done because I'm thrashing on secondary cache. So for me, a 288 second process, if it's over 10%, so that's 30 seconds, so that'd be about 220 seconds, or 320. If I got above 320 seconds, I would consider that an inefficient thrashing situation. I've always used a 10% rule. 10% of my time is not productive. I call that thrashing. Now if I multi-thread, there's a little bit chart, the last chart in the workbook. False cache sharing is going to look the same, except it's a multi-threaded application instead of single-threaded. And these other parameters are going to go up with it. The 31, 28, and 29 are also going to go up with 26 and 27. This is the result. Whereas event 31 is the trigger. So event 31 says, I just wrote to a cache line that's being shared by other CPUs. And I know it was shared because of directory memory. So an event 31 causes directory memory to be referenced to say which CPUs do I then tell it to reload its cache line. And then that signal is sent off to those CPUs with events 28 and 29 saying intervene into your secondary cache, invalidate the data. And then that other CPU results in the 26 and the 7. So in this example, they ran this program and they scaled it thread width wide. They went 1 thread, 2 thread, 4, 8, 16. Code 2 will also do this. And once they went past 2 threads wide, their throughput actually got worse than single threaded. And also what was going up before and after tuning, before the interventions, invalidations, and secondary cache misses were going up as my thread width went up. So I run the program 1 CPU, I run the program 2 CPUs, 3, 4, 5, 6, up to 16. And then I look at the counters that we were looking at a minute ago. After they tuned it, and in this case what they then did was trap on event 31, find where the variables are packed together, some reads and some writes, and regroup the data or pad it. And after they did that, they then got it tuned so that the ideal tune-up went 8 times faster, 16 CPUs wide. Now you can never get perfect scaling, which would be 16 being 16 CPUs wide, 16 times faster. There's always a little bit of communication cost. And in this case, there's a lot of communication cost with the false cache sharing story. So even when I optimize it, there's still a trade-off. It's called Amdahl's law in terms of how much speed up I can really get. So before, I like that. Obvious once you fix it. Once you find those variables, and again you had to trap on event 31 to find them, then we get, anyway, see the secondary cache misses and the interventions and validations are staying flat as my thread width went up. And again, that's because they isolated the read and write variables that were defined at the top of subroutines or global variables. So once I identify that I'm multi-threading and false cache sharing is my problem, then I go back to where we were. So we left off at hardware counter profiling. But I needed to run perfx-8 in the first place just to figure out what counter do I want to watch. Now unfortunately the command line has a whole bunch of useless counters. There's no reason to trap every time I do a graduated instruction or on every clock period. Those are completely useless. Trapping on misses might be useful, but the best one on the command line is TOB misses. Okay. And did we do that? Let's see, what's the one here that did that? Yeah. So the next line, next page shows where they ran it on ADI2, and then the TOB misses showed up again in Z Suite. So every time, in this case, they say the counter I'm going to watch is TOB misses. Then we set a counter overflow value. So it says every time the hardware counter goes above 257, trap where I am. Trigger a snap of where I am. Now that happened 22,000 times. Okay. So if I'd had the Perfx data report for this, I might have found out that 257 might be too small of a number and I might want to up it a little bit more. So 22,000 times I overflowed 257, and when I looked at it, 22,076 of those 22,088 were in Z Sweep. So Z Sweep is where I'm getting all of these hardware events. But I don't want to track on 26 or 7 because that's where I am in my program and somebody else told me to resynchronize my data. If it's secondary cache misses, I want to trap on event 31. So TOB misses, we're trapping on event 23 here. But not all, it might be helpful for you to trap on floating point so you can find out where am I spending all my floating point work. But again, not all of the counters are on the command line, so in that case you need to do your prof HWC. I probably should have put that up here. And when I do it that way, then I have two environment variables that say what counter number do I want and what counter overflow value do I want to use. So if I'm trying to isolate false cache sharing, I'm going to set the counter number to 31 and then set the overflow value to something that makes sense for what perfects it showed me. If you want to trap unloads, branches, and stores, those sorts of things might be relevant as well. But we're going to see what those actually are in a few minutes. So I'm using SSRun to get me top programs, subroutine names, perfects to figure out if am I productive or non-productive. These are the non-productive things in my service time.
Shouldn't the ACC, the account CMS command is -n for the codes that we're using?
You're saying act CMS and I was saying act com -n,
Right.
code name. But I also see that the file switch has occurred, so I've got to put var adm ACCT asterisk run.
Sort,
What was that?
get that peg at the sort group together.
Yeah, you can do sorts, or a B will go backwards, things like that.
The file that you put it over there is where is the information? The /var/adm?
That's the data that is being kept by the kernel for every
Okay.
process termination. So that's my input.
Okay.
And I'm using the star because I got more than one PAC file there now.
Then these are all consistent, aren't they? 38 got 64s.
You know, here's one that, again, I'm not looking at exit status, but here's one that doesn't look too bad. 2 threads wide. Each of those code 2MP jobs are going to be slightly different. Now, when I was looking at my data now, I'm going to take a look at the perf report I had here. And out of the 288 seconds again, 122 was floating point instructions, so I don't have a whole lot of cache misses in that one. Whereas some others may show up more. By the way, that plot that I showed you, I do it with every release, and it's 6.5.9 and beyond, it has changed its behavior. They have optimized the CPU scheduler. So here's my bottleneck curve again. nproc over here, which is going to be infinity. Unity over here. And let's just say number of CPUs right here. So in my bottleneck curve, I actually start losing some of my response as I get close to the number of CPUs due to check config daemons. And then at the actual number of CPUs, we were seeing that big bump. And then it looks something like that, maybe. Okay. Now, I actually went through a standard error file and I'm getting the same sort of data, but this was a 6.5.9 release. And now I'm getting completely different types of numbers.
659 or 679?
I think I meant 6.5.9. I'm not sure if that was the date that I took it or what. So look at the way that one's looking. In some cases, what I'm seeing now, this one is much bigger. I hit that wall and everything goes up. And in some of the newer ones, I'm just going to zoom in on this, see if we can see it here. Instead of being as clean as it was before, it's now actually, some of them are separating where you actually get 2. And the range is a much wider range now. Before, it plateaued up. Prior to 6.5.8 to 6.5.9, it actually had a plateau. Now you still have the ceiling of the plateau, but what's happening now is some of these processes are keeping their affinity and staying locked down much better than they did before. In other words, before the charts that I showed you earlier, everybody kind of lost affinity and they all slipped. Now I'm seeing where some of them are still keeping their affinity and the range is getting wider. So some stay locked down, so their affinity is staying stronger. What we're trying to do is avoid processes that are thrashing around in the system. So every time I get one of these releases, I run this experiment to see what my bottleneck shape looks like. And it's been getting more where some are getting stronger affinity and some are actually getting worse. So we're separating into two classes, those that get and those that fight for it their whole process life.
Almost like sawtooth in there, isn't it?
Good. Also on some of the systems I see changes between even and odd. Where if my queue length is twice the number of CPUs, it actually flips its behavior and stuff. You can see the even and odd ratios of the run queue to the CPUs within some of these charts. But in my toolkit, all that was, I had a whole bunch of reports that I ran. And this is just what it looked like, and then you get the compilation, and then there's the initial reports. So I can go back to the data and then see, here's my 282nd where I started. And go, this is the numbers I'm actually pulling out of this file to do this. Now if I have my way, eventually this data will get written into accounting records. It is a futures plan. And then I don't need perfects anymore. I can go to a global log, pull out all these numbers, and then identify the programs that have application problems, that have any of these problems. I'm checking multi-threaded version. Are you having trouble with the NQE command?
With the
Queue sub? Just do a module. If you got copy my .login, then you should have loaded the NQE module. But try a module load NQE, and that'll get the path and everything loaded right.
Yeah, it's a module NQE.
Module load NQE. I was going to go to 12:30 for lunch, and if it's okay, I'm just going to avoid a break. And what I'm doing now is getting into multi-threading. So I've submitted some multi-threaded applications and hoping that they work correctly. One of the problems I have with multi-threading now is that I need more memory. So I'm now starting to see some of my applications queue up because of memory not being available. So I got a perf, I got a probe, bring up top.
Yeah, 10 empty CPUs.
Yeah,
There they go.
that'll change very quickly
There they go.
as soon as the compilers finish.
Yeah.
So up till now, we've really been talking about single-threaded. In other words, one proc, LS, PWD, the normal type of stuff. Now for me, it was about 1985, 84, when Cray came out with a 2-CPU Cray, and one of the weather sites said, let's rewrite our application and put the northern hemisphere on one CPU and the southern hemisphere on the other CPU. And in those days we called it multitasking in the Cray world because the library routine names were task, create task and stuff like that. We call that multi-threading now. And there are 3 different styles of multi-threading. The first one was where I had to rewrite my application. Okay, and in rewriting my application, we called that macro tasking because you called library routines. That meant rewriting the application. Nobody wants to rewrite an application if they can avoid it. Now that original library has been standardized these days. There is only one standard for macro tasking. Anybody know what I'm talking about? MPI. That has grown into MPI. There's also PVM, but that's really not a standard. It's commonly used out there, but MPI is the application, or I should say the library interface to do multi-threading, where you actually have to call the library routines to do things.
It's PVM?
Parallel virtual machine. PVM came out of Oak Ridge, Tennessee. MPI has several flavors of it. Edinburgh University, Argonne Labs in Illinois, Los Alamos, and Livermore. Those are kind of, then there's also SGI Cray's MPI, and also there's a Pro MPI that's out there now. Now, a couple of advantages of MPI. First of all, it's compliant across platforms. I can put it on a large 128 CPU origin and use shared memory to communicate between things, or I can put it on a cluster of Pentium chips that's a Beowulf cluster and talk across network interfaces. The MPI libraries will worry about how I communicate between the different threads. Okay. The other advantage, other than the portability across platforms and everything, the other advantage is that MPI avoids false cache sharing. Because in an MPI situation, every thread is a separate process and cannot step on another process's variables. So the way MPI is written, when I rewrite it, I chunk up my data and pass it off to the other thread. And the breaking up of the data and the spawning of an independent process avoids false cache sharing. And with MPI, every thread spawned off, MPI run, you do an MPI run, there's a -NP, and then the number of processors that I want to, or number of threads I want to spawn off, which should be less than the number of CPUs you have. So that's basically the standard for rewriting applications nowadays. And this is more for scientific market. Then came along what was called microtasking. Microtasking is compiler directives. We let the compiler do the work for us. And microtasking now has a standard for its name called OpenMP. Now OpenMP, by the way, MPI was using fork to create the processes, whereas OpenMP is using the SPROC interface instead of fork to create its children. With OpenMP, you still have one PS entry per thread. And they share addresses. Share their address space. So when I went to multi-threading here, looks like I got some things that are finishing. Note that my memory resident was 23 meg, but my size is actually going up as I get more and more thread width. Right now I'm doing like 2 or 4 threads wide. As I go wider and wider, my virtual size also has to go up to cover the shared memory between all these different threads to account for it. Let me see if I've got a report back yet. Looks like I've got one. Not the one I want, but let's take a look at it anyways. I did get a report back. It's the Perfex report, but I wanted an SSRun report first. By the way, if I ever get my way, Perfex and SS Run would be in the same experiment. That's the way it worked on Craze. HPM would collect hardware Perfex data on a per subroutine basis, actually down to the do loop basis. And that's something that SGI hasn't done yet. So I'm going in and looking at my application. And in this case, it came out at 880 seconds. Oh, wait a second, I was at 288 before. Now I'm at 888, or 880. I'm worse than I was before. Not as bad as single-threaded, but still bad. But look what's at the top of the list. So 235, 235, and 220. 235, 235, that's 500, 600, 700 of my 800 seconds is on loads and branches. And that is barrier synchronization. Okay, that's what we were talking about here. As I go wider in thread width, this is going to get worse and worse. Okay. And again, this goes back to rewriting the application. It's not something I can do at the command line level to solve. Now, there are some administrative issues we'll talk about in CPU scheduling that can help me synchronize my barriers better, but let me save that for tomorrow. Multi-threaded applications are not designed or meant to run in the interactive timeshare band. They should be running under miser or real-time. So I'm looking at a multi-threaded version now, and I don't think I've got actual data here. Now, there was no JA report in that particular job example. I was trying to look at the timing for it. Since it's DAW, let me just try that one. Atcom-N code 2MD-UDAW. Okay, so it looks like in those examples, I've got several that ran now. Right here is a whole group of the same multi-threaded application. They all started at 11:35:34. Now, if I go to extended or CSA accounting, I can see PIDs and parent PIDs and tie them together. But with ATCOM, I can't. That data's not there. I've got 1, 2, 3, 4, 5, 6, 7, 8, and a parent thread that's watching over everything. And again, I'd have to look at the PIDs to figure that out. In fact, it looks like this is probably my parallel thread, or my master thread. So the entire group of processes took 302. Not so good considering I was 288, single-threaded. This one, however, came out at 263. Came out better. Again, the variance from run to run is barrier synchronization problems due to loads on the system. So for each one of these processes, note their sizes as well. 24 meg for most of them, except for the parent shepherd at 11 meg, and then the rest are all in the 23 meg. So these are the ones doing the actual work. And this is the ones saying, what are you all you guys doing? And then when you look at the actual service time, the one thread that got most of the work done was this one right here. 294 seconds, 121 seconds on this one, and the rest were 30, 40, or something like that. So this barely got past 2 threads wide. We're going to talk about this, that's where we're going right now, is dynamic threading versus static threads. So this is a multi-threaded group. And this was my micro-tasking situation. And in actuality, it is actually the third type, which is auto-tasking. Basically, the developer said, why should I rewrite my application? That takes too much time. Why should I even bother to tell the compiler what to do? Why can't it do it on its own? So they built pre-processors that look at your code and then stick the compiler directives in there for you. So auto-tasking is a pre-processor.
The fork is a request. That's what the fork does.
The fork is what creates a general process, yes.
Okay.
Any process is created with a fork.
Okay.
But OpenMP is going to use sproc.
Okay.
And auto-tasking is also going to use sproc. Now there's one other threading style in here. So auto-tasking is -PFA in the older days, which was a third-party product that you licensed that went through your source, stuck the compiler directives in there, and then the compiler would make that thing multi-threaded. And now we call it -APO. PFA was actually the third-party vendor, whereas APO was the Cray compiler technology being put into the MIPS compiler environment. So when you're using APO, you're using the original Cray one, which actually I think came from Cook Associates originally. There's one other threading style that's called P-threads. And P-threads is going to do an NSPROC to create its process. And with P-threads, I find this more commonly in the network area, browsers, more common in the C area. It doesn't mean that you don't have scientific codes doing P-threads, but most of them are doing these. In fact, in the weather environment, there's a program called MM5, and it spawns MPI tasks, and those MPI tasks then spawn OpenMP threads. So you can use these in combination with each other. So you can be forking off children, you can be forking off MPI tasks, or you can be creating OpenMP processes. By the way, with P-threads, it's one entry per thread group, one PS entry per thread group. So here's my thread group. In this case, 2 of them did most of the work. Actually, I should say 3. This one, it looks like we went 2.5 CPUs wide, and the rest was kind of random. So I was going 8 wide by default, and I only got 2.5 CPUs. And the rest of the time was actually spent thrashing, saying, "Are you done with your work yet?" Let me see if a prof report has come back yet. Splat 425. So if the user comes to me with a SS run user time report, what did I say was going to be at the top of the list? There it is, empty slave, wait for work. Now this stuff will change depending upon what compiler release level you're running. I'm running a 7.2.1 compiler right now. Tomorrow I'm going to switch to the 7.3 compiler and we will see changes. For example, in this example, we only saw loads and branches. But in the 7.3 compiler, there's a store that's going on in there as well. So this stuff can change. They've changed the name of the subroutine to make it less obvious too. You got a question, Mark?
Oh, it's the 4th one down, or 5th one down.
There's another one here, which is my master, barrier master. That's the master thread. These are the ones waiting for their work. These are the children. And here's my real work. That's not so bad, but look at, I've got still 68% of my time, or 543 seconds, waiting for work to do. That's the clone tag. That's the best analogy I can think of. So it's non-productive. That's my synchronization time, the time it takes for me to communicate with all my other threads. The more threads I have, the more that's going to go up. And that's different than false cache sharing. So we're seeing now with barrier synchronization what's going on. Now let me see if I've got a program running. I'm going to code to MP-NQS. I'm going to modify and go 2 threads wide. Now let me make it 4 instead of 8. Now when I first found this 4 years ago, I could submit a code 2 single thread and come back much quicker than the multi-threaded version. And that's still true today. I have been able to get timings that were under the 200-second range, but the majority of them are still coming up over 200 seconds. And also, the more threads I create, the more of a problem. So that's why I've dropped it down to 4 threads wide. Now, I have a tool in my toolkit, shareware, that allows me to attach to a running process to look at its hardware counters. It's called perfspy instead of perfx. And until I have perfx data actually in, well, even if it was in accounting data, I could have a program running for days and I say, what's it doing? So I'm waiting for this compile to finish. Then I'll get a PID and then attach to it. basically my tar file, the shareware toolkits for all the pieces that I wish I had when I don't have them. There we are. So, -bin/perf/spy-a-y-x, and then I think it's the PID that I want. I'm going to pick 5507, and then the time interval that I want to pull it. So I've now attached to the process. Now, if the process had already grabbed the counters and was running under Perfx, then it's going to come up busy. So if they've got the counters, I can't take it from them. So now every 10 seconds, it's going to look at it and look at what's at the top of the list right away. My first 10-second sample, I had 3 seconds of loads, another 3 seconds of loads, another 3 seconds of decoded branches. So if I have a program that's been sitting there running for a while, and I know it's multi-threaded, I can attach to it with this and see what numbers are going up. Do I have 31, 28, 29, 26, 27 going up? Or do I have 2, 18, 6, 3, and 19 going up? What's going up in the list? So every 10 seconds, something is consuming that 10-second time. And we'd like it to be floating point. So where are we now? 50 seconds so far. 17 on branches, 15 on loads, another 15 on loads. 30, 45, 45 of the 49 seconds playing phone tag. Okay? So Perf Spy is something that I've been wanting to get standard with. It's an extremely useful tool for the administrator. I've been having you run it as a child of Perfx, but this allows me to actually get to it. Branches, loads. Okay? I'm just going to get out of that. So we had 79.85 seconds there. And 27 of it was decoded branches, 25 loads, another 25 on loads. Okay? So no matter what you do, I would hate to sell this customer more CPUs because that's not going to help them. In tuning this situation, multi-threaded applications have to be synchronizing better. A lot of that is code rewrite. Now I'm spending time on this because a lot of customers are finding the effect when they went from 6.2 to 6.5, multi-threaded applications were to your advantage in 6.2. But in 6.5, the CPU scheduler will penalize multi-threaded applications. And basically the scheduler is treating all these processes as the same scheduling unit, and they can't all get connected at the same time. They can't get to a conference phone call. They're playing phone tag with answering machines. Okay? So where are we in my slides here? So I've been using SSRun, Perfx, PerfSpy to look for inefficient effects. If my code 2 takes 2 weeks, adding more CPUs won't help, buying more memory won't help, fixing the application is the only thing you can do. Now, Ocean, code 2 is called Ocean, and that thing was rewritten. It's now known as POP, Parallel Ocean Program. And that's what they're using for El Nino modeling. And it's actually open source, so you can download it for free, run it on Linux, all that sort of thing. I want to cover a couple more slides and try to wrap up this chapter right now. But those are the 2 things I want you to do, is to run code 2 MPs and look for MP slave wait for work at the top of the list, and look for loads, branches, and stores possibly going to the top of the list. And I guess my next step here would have been, I'll just put it over here.
So what you're saying here is that when an application has those multi-thread various synchronizations problems, those parameters 2, 18, 6, 3, and 19, they're going up, right?
Right.
And in that case, the only thing you can do is to rewrite your application.
Except a couple other things I'll show you. But in general, fix the application first.
And what it needs to be fixed in the application? How do you?
That's all in algorithms. And we don't have the time to discuss that. And I'm not an expert on that. Every algorithm is different. Okay, but the engineer has to go in and figure out how do I communicate better.
So it would be a matter of communication with your CPUs?
Between your program threads. If I have more threads than CPUs, then I'm guaranteed that I can't talk to all threads at the same time. Okay.
So you have to put down your number of threads? Or not?
Yes, keeping them at a minimum. And that's the problem. Some people are going 512 wide, and actually it only scales 20 wide or something like that. So in the process of going through your initial setup of the system, you've got to test the application and figure out what its thread width is going to be best. And in our case, code 2, too wide. Once you go past 4, it's going to get worse rather than better.
Okay.
So this is what they talk about scaling. So application developers are rewriting the code so that it scales better. And that's a matter of how they communicate, how they break up their data, and things like that. But we're going to talk about how to solve it on the system side. And some of that is miser, some of that is a few other pieces we're going to talk about. But what I'm trying to do is just identify them so that I can tell the programmer. This, by the way, is going to be the largest variance. So when I was running single-threaded, it was 288 to 420. Once I run it multi-threaded, it was 166 to 2 weeks. So once I went into multi-threading, the barrier synchronization is the most painful and obvious problem out there. And customers going from 6.2 to 6.5 are finding it to be worse because the 6.5 CPU scheduler will not help a multi-threaded application. It will hurt it. It will intentionally say, I will not let this gang up on my interactive user. They don't want the multi-threaded codes to take CPU cycles away from interactive response. So that's why they have miser and real-time and CPU sets, things like that. Or run-on. If it's single-threaded, I can lock it down with run-on as well. Let me come back to multi-threading here in a few more minutes. Just want to go through a couple more slides here. So this is now getting into memory. And in the memory area, we have the text portion, which is our executable. We have the data segment. This is where I'm allocating my heap with mallocs. Whenever I do a malloc, I'm growing or shrinking the data segment. I have the stack segment. And the stack is where my operating system and libraries keep track of my subroutines. As I call a subroutine, I save my prior subroutine's environment into the stack. So every time I jump, I push something onto the stack. And every time I return, I get the information from the stack and restart from that information. Now when I multi-thread, the stack is going to go up because all these threads have to share the stack segment. The more threads wide I go, the quicker I'm going to hit stack segment errors. And that's where I can start running out of memory again. So I may have a small memory machine and I say go 120 threads wide, and it's going to create a virtual memory reservation for 120 threads on the stack and hit a limit. So as your thread width goes higher, your stack requirements are going to go up as well. So if I start running code 2 multi-threaded 32 wide, I won't have enough virtual memory to even get that thing running. I'll have to add virtual swap or something like that. And we'll try running a 16 thread wide code 2 and see what it looks like. Third piece is my shared libraries, and the fourth piece might be memory mapped files. Now the command size simply tells me about the binary. So the size command ignores malloc information. It just goes to the static what was built by the application. So with size we get the name of the piece of the program. So there's my text piece, .text, dynamic symbols, various other pieces that the executables are using. Down here is read-only data, my literals. And finally down here, the last one, BSS, is my blank common space. BSS space is kind of a Fortran original name, which is basically my scratch memory space. Blank zero common, a variety of older names that they had for it. So when I do a malloc, it's the BSS space that's going to grow and shrink. Okay, so if I malloc up, it's going to grow, and I can also release with malloc and go back down, and then it's going to shrink again. But this is what the binary is showing me. So size neglects mallocs. So BSS space, block storage. Programs may not use all the block storage space. That's what I call the sparse matrix solver. Code 4 is a sparse matrix solver. I've got it configured for 1 gig of memory, but it's only using 400 meg. So the rest, 600 meg, was reserved but never allocated. So I malloced 1 meg, or 1 gig, but in terms of my data pattern references, I only referenced 400 meg of the process. And again, logical swap, this is where we had the problem. Logical swap can't keep track of the virtual versus the physical that the program actually needs. And it could prevent programs from executing even when resources are available. So that's the problem we had here. We're going to see that when I multi-thread code 2MP, that my memory reservations are starting to go up. I'm not really using the space, and my memory availability is going to go down, even though I'm not really using it. It's a reservation, not an allocation. So this is what I talked about yesterday. When I run out of memory, if I exceed the data or virtual memory user limits, I get a return on my system call. My malloc will return an eNoMem. If you did a P error on it, it would then print out no resource available. If I exceed my stack size, we get a segmentation fault. Remember seeing a segmentation fault yesterday? And if I run out of logical memory, out of virtual memory, and virtual swap is off, I get eNoMem. But yesterday we turned virtual swap on so that I could keep going, because code 2MP and code 4 have a lot of virtual memory reservation that they never use. So if virtual swap is on, it's a runtime error. The kernel will kill the largest memory consumer in the process table. It'll also take a decision about how long it's been since it started and whether it's a parent or a child. It'll kill children before it kills parents. I tried to explain that to my son last night. Forking children and killing children before parents and stuff. He didn't like the comment.
I had a conversation involving killing children whenever, and my mother was in the room, and I got scolded about talking about that in front of small children.
Yeah. I have a 12-year-old neighbor that is already loading Sushi Linux on his system and learning Linux, so we talk about these things. So that's a little bit about the memory. Going on, we're going to come back to this Friday, but there's page migration. There are counters in the hub chips that say every time I go off node for a page, count it. And if the off node references go over a threshold, I can then tell the kernel, move this page into my local memory. So that's called page migration. Draw a line through this though. The block transfer engine still is not working for page migration. Block transfer engine is part of the hub chip. And it is used for a couple other things. Number one was B0 to create pages. Number two is a routine called bcopy, which moves memory to memory to shuffle memory pages around. For example, every time I do I/O, I go through buffer cache. So bcopy moves it from user space to kernel space, or vice versa. And remember those performance events we were experiencing yesterday where it stalled for a few seconds and then came back? I was trying to create 2 gig of code 4's pages and still trying to use bcopy to get VI and LS and things like that through the system. The third thing that this block transfer engine is used for is called XPC, and this is for make part traffic. When I'm running NFS in a partitioned file system, NFS will go across the internal routers rather than go out onto the network. So I can take a 128 CPU system, split it into 4 32s, and put up NFS, and all the NFS traffic will be across the internal routers and will avoid going out onto the network itself. And frankly, that is giving extremely fast NFS performance, because you don't have the TCP stack to deal with or any of the network overhead of handling network protocols. So it's a shortcut, and they call it XPC. So any I/O that goes between the systems, any network I/O is using that. And last one is page migration, but it's been broken and not used. So I don't know the latest status on that one, but we're not using the block transfer engine yet. There's a way with Systune to turn the stuff on and off. So even in Systune, you can say don't use BTE. There are BTE underscore variables to say don't use the block transfer engine to create pages. That'll slow down memory allocation, but may prevent it choking out file system buffer cache. Okay. Or if page allocation is critical and you're not I/O bound, maybe you're going to turn off bcopy using the block transfer engine.
Now, the block transfer engine itself is hardware or software?
It's hardware firmware.
Okay.
So it's a function of the hub chip itself. And for us old timers, it was a vector register transfer that we used in Cray. We went through V0 and V1 to move memory to memory. So this is the same concept. It tells the hub chip, take this stream of memory and redirect it to it, or move it to a different memory location. Now there's another thing called page replication, and frankly that's been broken. The only thing replicated is the kernel. So there's a copy of the kernel on every node board. So if I take an interrupt, the interrupt handler for the kernel is on my node board. I do not have to go across routers to get to that code. Now we wanted page replication for applications as well. For example, a 128 CPU system, and I go 128 threads wide, and I'm going to do a cosine function. I don't want to sit there pounding on what they're calling here interconnect loads. I like to call a node conflict. Instead of a bank conflict, I have node conflicts. So if that subroutine is off on one node and 128 CPUs keep going to that one node to get that subroutine, that becomes a hotspot in the interconnect. So I'd rather waste memory and have a copy of that cosine function sitting in my local application and undo shared text. That's what replication is about. But it was panicking the system and they turned off page replication, but there are still documents that refer to it. There's still a man page to it. Now I can also give the operating system suggestions with compiler directives or dplays to say place my pages in a certain area. And I already talked about page coalescing a little bit. When I go to multiple page sizes, there is a coalesce daemon that's going to try to maintain targets. So it may pull together a bunch of small pages and then put them into a large page group. So you set up the percentage of targets you want for different page sizes. And you say, I want 25% to be 16K, I want 30% to be 16 meg, I want 10% to be 64K. And the coalesce daemon is trying to achieve those targets. That's what I call garbage collection. Basically shuffling stuff around in memory so that we clean up the empty spaces, make the empty spaces bigger. The disadvantage though is shuffling all that stuff around. So turning on large pages, I said earlier, could be a disadvantage. If I'm going to go to larger page sizes, my intent is to reduce TLB misses. So if I'll up my page sizes with dplays or with the application, I better see event 23 go down repeatedly. So I run it 5 times before and run it 5 times after, and I see a clear drop in TLB misses. If not, larger page sizes will probably hurt me more than help me. Because now coalesce daemon has CPU time being consumed, and it's sitting there shuffling memory around, and it's tying up the block transfer engine, and it's loading down the system, adding to the load problem. So it may or may not help you. And again, if I'm sequentially striding through data, it probably will. But if I'm doing gather scatter through memory, then it may be a disadvantage to me. So our new systems, again, we talked earlier, 4K or 16K, depending upon the bit size of the kernel. 32-bit kernels are 4K, 64-bit kernels are 16K. That's my base page size. And no matter what I do with this stuff, it does not affect the swapping out or the swapping in. That's still 16K byte type activity. So when I miss a page, even if I go to a 16 meg page, I'm still going to bring it in 16K byte chunks.
So how exactly does swapping is? You keep the same.
Because it's not a swap issue, it's a CPU service time issue of TLB misses going down. Because every time I can't find the page, I have to ask the kernel, look up the page for me. Okay, so if I go to larger pages, I have less TLB addresses describing all my data. And I have a better chance of fitting them all into my secondary, into my TLB buffer. So the purpose of large pages is to reduce the CPU service time I spend asking the kernel to find the page for me. I could have 1,000 pages, or I could go to 16 meg and maybe get it down to 200 pages, and it's a lot easier to work with 200 TLB addresses than 1,000 TLB addresses. So going to larger pages has to reduce this. If it doesn't, you're not helping yourself at all. So the default is 16K, and I can go 64, 256, 1, 4, 16. Now in my example with code 2, it was cache misses. TLB misses was the lowest piece because it was fitting into my secondary cache. So my code 2 does not have this problem. Code 4 doesn't really show TLB misses being high either. But again, a lot of that has to do with how I stride. I can change code 4 and stride through it in a gather-scatter type of fashion, and that could be bad. So in this example, dplace can then be used to change my page size. So I'd say dplace, the data page size, in this case they up to 64, and the stack page size, they also up to 64. And then the application runs as a child of dplace. So this is unique to IRIX, being able to specify larger page sizes.
So when you have when there is all these pages in memory, you have like 60 meg, what it seems like in one chunk is put it more than, different kind of pages on.
So when I go to the TLB buffer and I get the address, I now with that address can describe 16 meg instead of 16K. So if all my data is contiguous in that 16 meg, I don't have to take a TLB miss. I just go through a larger address space. So going to larger page size allows me to describe a larger memory with a TLB address. So if I were a 16 meg program, at 16K I may have lots of TLB buffers to describe everything. But my 16, if I went to 16 meg and codes 1 and 3 that are smaller than that, they won't take any TLB misses. It will take one TLB address to describe everything about the program. So a small memory program won't help at all from this. But it's basically if TLB misses, I said, with TLB misses, first of all try to rearrange the data, and that's what that tuning guide I showed you in TechPubs was for. And if that has been optimized, larger pages might help. The disadvantage is the garbage collection. That now I've got something to constantly keep my memory compacted properly. Now there is a command called dprof. Dprof basically tells me here's my virtual address, here's my thread number, here's the number of times I've read and written my data. I don't want to emphasize this at all, it's going to go away in the future. But what we then did was plot. So they ran dprof, ran the application underneath dprof, and then plotted all their memory references. So down here is my virtual address space, and over here is the number of times that I hit the page. And then I've got 4 threads, and dprof is relevant for multi-threaded. I don't care about single-threaded, but dprof is for multi-threaded applications. Now this display shows poor distribution. Why is that? What makes this look like a poor distribution? Let's look at a good distribution. So here's a different program, but this is marked as good distribution. So what's the general difference you see between the two? With this one, I'm rotating. No, thread 0 is in its own address range, thread 1 is its own, and they're rotating. They have separated the data structure such that each thread is working in its own memory address range. Again, this goes back to programming and how my arrays have been laid out. If I take a look at the bad one, every thread is stepping on every address. So there's no interleaving going on in here. Every thread has data spread across every address, and every thread is stepping on every address. Now there are going to be some areas where threads are going to compete, for example, global areas, getting to global counters. So right in here, for example, there is some overlapping, but there'll always be some.
That's what's going to give you your invalid cache lines and all that other stuff to slow you down?
No,
Probably.
no, this is just how this is going to prevent, for example, page migration. I guess in a way it would indicate that, but in this situation, these are usually just reads or writes, or I don't have a read or write on the same line. Okay. So this is really more just interleaving my data so that I'm not choking on one memory port. It's going to be memory access times that I'm talking about. I don't think it's really going to help you in your secondary cache in this area. But the point just being that when you multi-thread, you don't want one thread stepping on all the pages for all the other threads. So in this example, they are interleaved, except for right in here, there's a page that is being shared by both threads, where they're global variables or something. Whereas in the other example, every page is being pounded on, not necessarily pounded on 20 or 30 times, but every thread is going across all pages.